So let's take a look through some applications working with power functions. And let's talk about some terminology here to begin that might come up in some of the work that you do. So something that comes up is this idea of varies directly and varies inversely. And this will change how y is relating with x. Is it y equals just a constant multiplying with x? Or is it y is multiplying with a constant times 1 over x? So inversely is going to bring through a 1 over x, and that's what we're going to see here. Whereas directly, we'll just see it relating directly with x without the fraction. So if it's relating to x as a constant, then what we'll have is this scenario of just y equals some constant times x. But what we can also have as it relates to power functions is that y varies directly with a power of x. And with that, what's going to change our formula is going to be y is equal to a constant times x raised to a power. So difference of an exponent versus not an exponent is them saying whether it's varies directly with a power of x or just with x. Now varies inversely with x if it's just directly with, or not directly rather, sorry, bad terminology, but if y varies inversely with just x, then what we would have is y equals a constant divided by x. So that's where the inversely comes in. It brings through x as a denominator. And then if we change this to y varies inversely with a power of x, then we have that same form, but now we could have an exponent on x. So it's a constant divided by xcn. So take a look out for that terminology of varies directly or varies inversely, and that will help you set up some functions. So let's take a look at two scenarios here with power functions. So we have the incubation time for a bird's egg is a function of its mass and has been determined as I of m equals 12m to the 2.17. Sorry, 0.217, there we go, where m is measured in grams and I is in days. And I'm going to even put that to the side. So m is the weight in grams, and I is the number of days of incubation. Okay, so calculate the incubation time to the nearest day for the wren whose egg weighs about 2.5 grams. So starting with the wren here, we want to find I, and we're plugging in this mass of 2.5. So we're taking 12 times the 2.5 raised to a power of 0.217, and we'll go ahead and put that in a calculator. So lots of calculators going here. So 12 times 2.5 to a power of 0.217, so 14.64. And we're going to go ahead and round this to the nearest day, so rounding it up, that would be about 15 days. And now for the goose with an egg weight of 46 grams. So we're going to take that same formula, but plug in 46 instead of 2.5. Which, going back to our calculator, I'm just going to make the edit, take out the 2.5 and put in 46 for 27.54. Which is about 28 days. Okay, so there's using our power function to make calculations. Then we get this information. During incubation, birds' eggs lose water vapor through their porous shells. The rate of water loss from the egg is also a function of its mass and appears to follow the rule W of m equals 0.015 m to the 0.742 in grams per day. So we're bringing in a new variable that's in grams per day. Combine the functions I of m and W of m to calculate the fraction of the initial egg mass that is lost during the entire incubation period. So what we want to end up with is a fraction of how much is lost in grams versus, or rather out of, the initial mass in grams. We want to see what that fraction is. So to know how much weight was lost, what we're going to do is, we have this information about grams per day. What we want to know is, what is the total number of grams? So what we could do is, where I is in terms of days, if we multiply that by that rate of loss of grams per day, that'll give us information just in terms of grams lost. So if we know how many days it's gone for, and then we multiply that by this rate of so many grams per day, multiplying those together will just leave us with those grams of loss. So that's what we're going to do. We're going to multiply our two functions together, and then we'll create a ratio. So we're going to take I of m times W of m, which will be taking 12m to the 0.217 times 0.015 m to the 0.742. And combining those together, so a 12 times 0.015 is a 0.18. And we'll have m and 0.217 plus that exponent 0.742 to combine those together for a 0.959. So what this is doing is, if we plug in the mass of the egg, we're calculating the overall grams lost. So what we want to do is, going back to what we're interested in, which is this fraction, we want to know the ratio of how much is lost compared to the mass of the egg overall. So our calculation for how much was lost was a 0.18, m 0.959, and then we're going to divide this by just mass, which would just be m. So this fraction, we would have a 0.18 m, and then 0.959 minus 1 for a negative 0.041. So this right here is the fraction of the initial egg mass that is lost during the entire incubation period. So explain why your result shows that most eggs lose about 18% of their mass during incubation. Well, we're getting this calculation of mass right here, and every time we're applying a 0.18 multiplying to it. So that right there tells me we're taking 18% of the mass. So that's just kind of reading the formula and seeing that value up front as a decimal is taking a fraction, or rather taking a percentage of our total value. Okay, another thing we're going to look at is modeling, and with this we are going to use Desmos. So we have this data here for when an automobile accelerates, the power P needed to overcome air resistance varies directly with a power of the speed V. So varies directly, I want to make note of that because we should have this direct relationship between the two. And we're going to be writing this as a power function. So what we want to do is create a function P of V equals, and then we'll have some constant times our variable, and then we're going to have some exponent. So lots of unknowns here that we need to fill in the blank for, and that's where Desmos is going to help us. So this is similar to what we did with fitting data to a linear model, but now we're going to be using a power function. So let's go to a graphing calculator here with Desmos, and then we're going to add in a table, and we're going to put in our x and y values. So x1 I'm going to call v, so that'll be 10, 20, 30, 40, and then 355, 2840, 9585, 22720. And if we scroll way out, we could probably start to see the hints of this function being graphed. But those are some pretty big values, so our dots are out there, but we could adjust the scale to see it, but we don't really need to look at it. So I want to fit this format right here. So what I want is a function for our outputs, which is y1. So I'm going to go y1 tilde, so my little squiggle there. I have some unknown. I'm going to go ahead and call that a times, and then our input value, which we put in our table as x1, and then we're raising that to a power of some unknown n. And what this is going to do is fit values to the data so that it's the best fit, giving us values for a and n right there. So I plugged in values into the table, and then I'm going to go ahead and write this on my paper so that you can use it again. I plugged in y1 tilde a times x1 to the power of n, because we have a power function. And just so you know, say this had said varies inversely. If it had said varies inversely, what would have changed is where our exponent raised to the power appears. So I would have written it as y1 tilde a over x1 to the n. So if it was inversely, x1 to the n would go in the denominator. But since this was varies directly, we didn't have to divide. Okay, so what we're going to do is rewrite our function using the values that Desmos is giving us. So we found a is 0.355 and n is a 3. That's telling me a cubic function is the best fit for this kind of data. So find the speed that requires 50,000 watts of power. So if P is 50,000, what I want to do is solve 50,000 equals 0.355 V cubed. So dividing both sides by 0.355, so 50,000 divided by 0.355 is a messy number, but let's go ahead and write this down. 140,845.0704. And then to get rid of that exponent of 3, we're going to raise both sides to the 1/3 power, or you could think of it as taking the cube root of both sides. And so in my calculator, I'm going to take that previous answer and raise it to the 1/3 power, which is 52.0292, which is about 52 miles per hour. So the speed that requires 50,000 watts of power would be 52 miles per hour. If you increase your speed by 50%, by what factor does the power requirement increase? So this is a little interesting, but we can do this here. So we have our function 0.355 V to the 3rd power. So if our original speed is V and we want to increase it by 50%, what we're really saying is that we want 150% of that speed. 100% preserves that initial value that we have, and then with a 50% increase, that's what we're adding on to the 100%. And another way I think of this is like if we just took 100% of a value, it ends up exactly the same. But as soon as we add on, we're increasing that value. And similarly, we could take away, like if I wanted to take away 2%, we could bump it down. But 100% is kind of our initial spot, and then we go up or down from there. So what this tells me is I want to take 1.5 times V to show a 50% increase. So let's see how our function is going to change if I plug in 1.5 V. So P of 1.5 V, so if we increase by 50%, we're going to have 0.355, 1.5 V in parentheses raised to the 3rd power. which means we have 0.355 times 1.5 to the third power, which is a 3.375. And then we still have v cubed. So our new piece here is this multiplication of 3.375. So by what factor does the power requirement increase? It increases by a factor of 3.375. So that would be the factor that we're multiplying by based on how our original function compares to our new function with the 1.5 plugged in.